we're very happy to have Abhiram Kidambi, who is coming to visiting us from IKMU, and who will be talking about modularity from supergravity.
Yeah, so thank you, Boris, and thank you, Bruno, for the kind introduction. In case I'm not audible, please just feel free to let me or somebody know, and I can talk a bit louder. This talk is more or less something that we worked on quite a bit in the past with Rencontres, who's here in the audience, and Samir Murthy, and Tim Vaz and Abhishek Chaudhary, but then we took a break from it, and then we resumed working on the idea. So right now it's currently based on work in progress with Suresh Nampuri, Gabriel Cardoso, and Marty Rosello, who are in Lisbon, and Val, who is here / Leuven. Yeah, so it's based on a lot of different ideas that we are we've been thinking about and trying to solve for the case of n=4 string compactifications. Basically, what we want to understand is what are the spectrum of index BPS states for the n=4 string supergravities. Okay, so the key part of the key idea of the talk will be as follows. I'm going to make this as generic as possible, and I know many of you here are experts in this topic, but please do bear with me. So the first part is going to be talking about how we look at black holes in string theory, at least from the point of view of this talk, and how to construct the associated BPS partition functions. For the sake of this talk, when I say BPS partition functions, I'm going to use it interchangeably with the notion of index BPS partition functions. They're the same thing for me in this talk. And we're going to be looking at how automorphic forms play a huge role and what kind of automorphic forms enter BPS counting functions in this compactification. And we're going to start understanding where the origin of this black hole entropy is, both from conformal field theory side, which sets up the motivation of the problem, and then we want to understand how we can reconcile the so-called modular symmetry. It's automorphic symmetry that shows up when you want to look at it from the supergravity side. So for those of you who are more interested in the physics side of this basically is going to be how supergravity, or we're going to go towards the question of how supergravity can in principle see this modularity of BPS partition functions. And for the more mathematically oriented, it's in some sense a very nice physics-related dictionary, physics-motivated dictionary between number theory and geometry by BPS states. Okay. So let's go over the motivation. This is the part where it goes very, very slow. I have 1 hour for my talk, right? Okay. So we know that classically black holes have no entropy. And that was one of the bigger challenges in the 1970s to understand how to reconcile this with the laws of thermodynamics as we know it. And that led to a paradigm shift in studying black holes, and that led to the so-called semi-classical way of thinking about black hole entropy, which is that in the semi-classical event, black holes do have an entropy. And the semi-classical entropy is something that was studied by Begerstein and Hawking, and it scales as the area of a black hole. And this is something that is a universal result. It doesn't matter which black hole you look at or what quantum field theory you put on the black hole, or you put the black hole in. You will always find that if you compute the area using QT equals spacetime, it's always going to go as area over 4 G Newton. So it's in some sense a universal result. And in some sense, this is basically why we also are motivated to think about the information paradox as being something that's so closely related to the event horizon that that there's a notion of entropy information actually localized on the event horizon itself. So we want to ask the question, well, if we think about the fact that the laws of black hole thermodynamics are in cahoots with the laws of, in association with the laws of thermodynamics as we know it, you could ask the question if there is a partition function or a microstate partition function Z, such that the log of this partition function really tells you, reproduces the area log. Okay? But this paradigm is not entirely sufficient because the Begerstein-Hawking entropy is a semi-classical one, which means that it has not received any sort of quantum corrections. So In principle, this means that it works only when the radius of the black hole is very, very large. So if you go to a fully string theory limit, if you consider things like higher derivative corrections, large charge corrections, this paradigm is not quite sufficient. Okay, so you want to ask a different question now. Because if you look at the quantum entropy of a black hole, well, it receives corrections from other subleading saddles in quantum gravity. And you want to ask the question, well, you've got these subleading terms, which are often model dependent. So they depend on the black hole, they depend on the QT. But this guy is a universal term. So ask the same question again. Oops. Is there a partition function, Z black hole, such that, or which gives the microstates of the black hole, such that the log of this microstate generating function is the entropy of the black hole. In other words, what is the quantum partition function of a black hole? And of course, there's a more pertinent question you could ask, and this is what people in Sapler are very, very famous for, which is to understand what the corresponding geometry is for a given state of a partition function. Okay. The difficulty is that computing the quantum entropy requires your ability to see all the saddle points in the Euclidean quantum gravity path integral. And you cannot evaluate this in classical. In string theory, you can do this, however. And before you do that, it's usually useful to understand how you can construct a black hole in string theory. Okay, so this is a very, very, it's a very introductory picture. So in string theory, the key ingredients are going to be your strings and the extended cyclonic objects known as braids. We're going to be looking at black holes constructed from D braids. I'll tell you what models exactly we're looking at in just a minute. At low string coupling, the D braids have no back reaction to gravity. So if you increase the string coupling, the D braids back react, and they couple to the background spacetime, and eventually spacetime in the supergravity limit is something that becomes similar. So you can model it with a black hole in supergravity. At the same time, at low string coupling, the dynamics of the system is really given by the dynamics of the world volume of the D braids. So it's going to be a conformal free theory or something that lives on the world volume. So this is the breakdown of the problem based on the dualities. You can work in principle where the G string is very small, and you can try to ask the question, well, can I describe the theory on a world volume level, or can I go to high G string and describe it from supergravity? This is not always possible. It's not always sensible to ask this question, because what you want is a limit where the G string greater than 1, you have a black hole in supergravity. This is not the actual Penrose diagram of the black hole, right? It's just the Penrose diagram of a Rice-Knudsen black hole, which is the one that we're going to study. So that's why I put this back. But it's not the Penrose diagram of an extreme radius Rice-Knudsen black hole that comes out of supergravity. Okay, so it's a very pictorial description. But in the G string equals 0 limit, the world volume theory is this superconformity theory that describes the motion of D braids. So you can ask the question, well, can I just tune G string and then relate these two limits? Well, that's not obvious possible, because in string theory, the number of strings grows as, well, if you take the mass of your state, it grows as e to the m, where m is the number of black holes in supergravity. M is the mass, so the number of black hole states grows as e to the m squared in supergravity, whereas you want this number of string states, which grows as e to the m. So if you try to get a sort of match between the growth of degeneracies between how the string state scales and how the black hole state scales, well, this is going to be a difficult problem. You cannot reconcile these two scalings. That is why there are some nice suggestions that there's some denormalization which could, in principle, help you out over here, but we don't really know what kind of a mechanism this actually is. So what you could do instead is work in a limit where you don't have to worry about these things, where the states that you're looking at, the black holes you're looking at, are protected by certain non-denormalization terms. And that's precisely what happens when you look at string theory, BPS states in string theory. So when you look at the BPS limit of your problem, this scaling between G string is 0 to very large G string is actually a protected quantity, because BPS states, the spectrum of BPS states is independent of the value of G string. So you could always tune. I've committed the cardinal sin.
Just press again.
Okay, so you can always tune between GS equals 0 and GS much greater than 1. And what you're now looking at is the spectrum of BPS states. Well, here, the BPS state, basically what happens is that as you tune them, they just collapse into black holes. Here, so, but because the spectrum is going to be the same as the spectrum as at extreme equals 0, you could just compute the spectrum over here, right? So you can, in principle, look at the world volume theory of the deep range, which is like with conformal field theory, and you can ask, well, can I compute it in terms of an ADS supergravity? And the ADS part of it is because you're looking at a Rice-Nordstrom black hole, which has to be the solution that you look at in string theory, because you just can't, in string theory, you can't just have a quantum black hole with just the mass. You have to give it charges to make sure it's stable, which makes it Rice-Nordstrom black hole. And the near horizon of it is always going to be ADS. So you move the near horizon with the Rice-Nordstrom, so it gives you an ADS space-time, and you've got a conformal field theory, which lives in one dimension less. So you can ask, well, now it's a well-known question about the question that is there a conformal field theory partition function of BPS states such that the log, it's exactly it reproduces the black hole entropy precisely at all orders of correction. In fact, the area of 4G law is actually, that's something that's almost canonized in string theory at this point. This was something that was derived for BPS solutions, and as the leading growth of states in the so-called Hardy limit of the world sheet theory in K3 plus S1 compactification applied to the string theory by Strominger and Alpha. But what we want to ask now is, well, can you do this for all the corrections? So this is again, this is where it's important to understand which model you're looking at. And mostly we're going to be considering two different kinds of models to make the, it's important to first understand the relation between the geometry side, that is the black hole side, and the conformal field theory side. And there's a very nice way to look at it in terms of the N=A theory, where it's sort of a relatively clean description. But of course, if you want to go to N=4 case, which is half maximum supersymmetry, the problem is not so clean, and that's because K3 breaks supersymmetry for you. So, and in principle, you have non-trivial effects like wall crossing that you have to worry about. So, of course, you could be even more braver and go straight N=2 limit, like Boris often does. But I like to, we still want to work at N=4 case at this point. So we have two different systems that we want to consider. This one is just going to be sort of an example to motivate the setup of the idea. In N=8 case, we consider so-called D1, D5 setup. So you take a system of D1 brains, D5 brains with some momentum along and motion along a KK monopole background, compactified on cycles of a T6, which we immediately just break down as T4 cross S1 tilde. And the D1 brain, there's a D1 brain that sits on this S1, there's a D5 brain that sits on these guys over here, and you have n units of momentum along one of the S1s and L units of momentum along the other S1. And this whole, there's a motion, there's the whole motion with respect to S1 along the KK monopole background. So for this entire setup, there's an associated moduli space, and you could ask, well, is there a moduli space invariant way of counting these black holes? And for that, it's very important, it's useful to consider the so-called charge invariant. So regardless of where you are in moduli space, there's a quantity that you can construct which remains invariant regardless of what modular transformations do, and that is only 4n minus L squared. The same thing works for the N=4 case, but the only difference is that you sort of replace the K3 by, or T4 by K3. But now you also have to consider that the setup is a bit more complicated, where you can insert Q1 number of D1 brains on the S1, you can insert Q5 number of D5 brains on K3 plus S1 tilde, and you can have momenta on S1, S1 tilde, and motion on KK monopole background. And that gives you a charge invariant, which is now 4mn minus L squared. It's kind of, you can quite easily see that, well, this sort of is minus the discriminant of a binary quadratic form, because in binary quadratic forms, you've got charge discriminants which are B squared minus 4ac. And it actually is, they are related. Like, you know, this can be a question you could ask a bit later on, and they are actually very related to each other. So this is the setup of the problem that we are going to be looking at.
Yes, you could also take Q1 and Q5, D1 and 5 brains on the N side, and we would have the same formula.
Exactly, yeah. Yeah, but there, this M also has a more subtle meaning in T1 because the Jacobi form obviously has index 1, so we'll come to this the subtlety later. Okay, so basically, if you want to study these four-dimensional black holes, as we've seen before, is that you need to compactly pack away these extra dimensions in string theory by wrapping these deep rings or so-called cycles of scalar diameter, T3 or T6 times T2. And in this compactified picture, the gravitational part of the black hole can be either ADS3 or if it's extremal, can be ADS2. And the Rorschach part is this two-dimensional or one-dimensional superconform field theory. So computing the partition function of such black holes is therefore the same as computing the BPS partition function on the two-dimensional conform field theory. Okay. So firstly, we have to understand why or how. So it's basically akin to doing loop calculation with two-dimensional CFT. So you have to have functions which behave in a very certain way under the combinations of these genus G-Riemann surfaces. Technically, we only are interested in one, but in the special case of n equals 4 string theory, we also have to worry about genus 2 Riemann surface. And the reason is something that I don't think we understand very well. It's a conjecture as to why we get these 2 Riemann surfaces. Okay, so now we are at the stage where we want to consider these so-called automorphic forms. Well, automorphic forms are basically just complex functions that are defined for that take it from for a topological group maps you to C, such that a bunch of these properties are satisfied. The most important ones are 1 and 3 for us, because the first property tells you that has some nice transformation properties under a discrete subgroup of G. And basically, the function f has some growth properties as you approach the domain of the boundary of the domain of topological group G. That's a pretty, how do you say? It's a nice definition, but not very. It's not quite useful. But what you could do is start looking at what groups G you want to look at. Well, you can look at the group where G is your SL2R and then your gamma is your SL2Z. And in this case, you have the so-called modular forms, classic ones that we study in string theory. So this is the so-called partition functions that live on genus 1 first. So here you can think of the upper half plane, which is a set of complex numbers which have imaginary part as greater than 0. And the holomorphic modular form of weight, usually holomorphic modular forms are always even weight objects. So holomorphic modular form of weight k is basically a holomorphic function from this upper half plane onto C, such that there's transformation law f of a tau, f of tau goes to a tau plus b or c tau plus d, and standard stuff. And of course, f is bounded as tau goes to infinity. So these are the 1 and 3 properties that are relevant for us. You could also worry about the property number 2, but we don't. Yeah.
Sorry, I'm a bit confused by the definition. Is that f is a function of G, and now you take the upper half plane being a portion of G, and does that have a group structure?
Sorry. I should have mentioned that this should be a discrete subgroup of G. Okay. Sorry, that's a typo.
Modular is different on G, which you may define as invariant function. There's an invariant function in your complex group.
Yeah, because in the definition it was a function.
Yeah, function of G.
Yeah, because it's not. This is the same as the weight.
Okay. Right. And of course, like there's something you can always notice here because the function is periodic in this variable tau, and f of tau goes to f tau plus 1 means that because of periodicity, you are allowed to do a Fourier expansion of this function. And the Fourier expansion is actually going to be the central object for us here. This is the key physical quantity that is going to play the role of, that's going to connect the supergravity and the CFT side of the so if you look at holomorphic modular forms, as you see, they form this very nice ring structure, which is that you could construct a whole vector space of modular forms of weight k, and they're all generated in terms of just these 2 functions, E4 and E6, which are the 2 Einstein series. And using this, you actually can construct all modular forms that live on SL2Z.
So this is product of E4 and E6.
Oh, sorry, this is another typo. It's your product times, not plus. Good. It's product of E4 times E6. Good. And then basically here you've got the example that we will be dealing with most in terms of in this talk is a so-called 24th power of the delegate eta function, which you can think of as E4 cubed minus E6 squared divided by 1/8. Now this is a weight 12 polymorphic modular form. But what the central figure is actually going to be the inverse of this function over here. So the moment you take the inverse, you get a 1 over counter, and then you actually get an exponential growth as you tend to infinity. And that exponential growth is really what you associate with the Kidambi formula, right? So this is, as you can recognize, this is the partition function for free bosons on a torus. It's so-called, it's an object known as a weakly holomorphic form. And for us, this is exactly the index partition function of perturbative half PPS states in the tetradic frame. So if you kind of work your way through string dualities, you can easily arrive at the idea that if you take the K3 cross C2 compactification of type 2 string theory, this is really just the index partition function of half PPS states in the compactification that we're looking at for n equals 4, for the n equals 4. So this is the K3 cross C2 compactification. So you could also then go to the G being SP2R. For me, 2 here refers to genus. I know from mathematician that sometimes there's ambiguity between 2 versus 2G. So these are actually going to be 4 by 4 matrices for me. And here the automorphic forms are going to be Siegel modular forms, where the Siegel modular group is the SP2Z is basically a set of 4 by 4 matrices that preserve under this transformation the symplectic form. And you consider the upper half plane of these 2 by 2 matrices who have imaginary part of tau and sigma greater than 0. And then the determinant of omega is greater than 0. And the Siegel modular form.
Sorry, the lower tau is a row.
Sorry.
What? The lower tau in this matrix is row.
Row. Sorry.
This is row variable. This is a row.
This is a row. Terrible. 2 typos already. So this is going to be a row. The Siegel modular form is basically a function from this H2 to the complex to the domain of complex numbers, which satisfies this relation of f of omega goes to A omega plus B plus C omega plus D inverse, and transformation guy is no longer C tau plus D as you had in the SP2Z case, but rather determinant of C omega plus D to K. A very famous example that we are going to be looking at is so-called Dijkgraaf-Verlinde-Verlinde form. But before we do that, let's look at the Fourier extensions. So these guys, they're also periodic functions in all the variables. Q is equal to pi I tau, P is equal to pi I sigma, and Y is equal to pi I z. They're still periodic, so you're still allowed to do a well-defined Fourier expansion. But what they also admit is something known as Fourier Jacobi expansion, which means that you can just expand in this row variable instead of tau sigma and rho. And what you get, what you have left over is going to be a function of just Q and L. There's typo everywhere. Sorry, this is, I don't understand. I think I might have been using a version which I'm not correcting properly. So this is phi ml p to the m. So I don't know why I have a QL over here. Sorry, this is it's p to the m. Sorry, I have quite a few typos here. I think anyway. So you have a function psi m now which sits in this expansion, and that guy is a Jacobi form of weight k and index m. Okay. So what exactly are these Jacobi forms? Well, you could think of them as being elliptic versions of your modular forms. So these are in some sense like the ones that are refined under your R charge in supersymmetry, and the index partition functions are basically just let's say, for example, you can have a partition function that's refined under this y to the 2j0, where y is equal to pi I z. You can think of it as some sense of elliptic variable. And you have Jacobi forms, which are automatic forms on SL2Z, and there's a semi-direct product of the Heisenberg group of R. And you actually, if you work with some elaborate number theory literature, particularly by Eichler and Zekier, it's usually referred to as the Jacobi group, which is SL2Z, semi-direct, the Heisenberg group Z2. And this actually has an important representation in understanding the BPS black holes. And we will look at that also a bit later. So Jacobi form of weight k and index m is a function from the upper half plane from C to C, where it transforms in this particular way. So it's got a modular transformation and it's got an elliptic transformation. So it's in some sense periodic in both the tau variable and the z variable. So it's sensitive uniform far away. It's periodic in both the tau and z variable. So they are functions that are periodic in both these arguments, and therefore these guys also admit a Fourier expansion.
So the lambda and mu have to be Z.
Yeah.
Sorry. Z. Z. Okay. You have this, the function that we're going to be interested in are so-called weak Jacobi forms. And these are the ones that are analogous to your weakly holomorphic modular forms that exhibit this exponential growth of degeneracy, just like in the weakly holomorphic case. And these guys are generated by rings. So you've got the E4, E6, and you've got phi minus 2, 1, which is just Jacobi theta square over 2 power 6, and 4 times this expression over here. Now this is a very nice result by actors like Feingold Rencontres, and the example that we will encounter most are the one that relate to phi minus 2, 1 and phi 0, 1. And in fact, this phi 0, 1 is exactly half the genus of the K3 surface. Okay, so if you do a Fourier expansion of these guys and you try to figure out how the coefficients grow as a function of 4n minus L squared, then these guys actually also exhibit an exponential growth in the galaxies. So analogous to your Crowdy-like formula. So basically the idea is that these automorphic forms actually correspond to physical partition functions. The modular forms guys, well, they will, in principle, in our story, will be the partition functions of black holes with electric or magnetic charge, but no area. The Jacobi forms will be the partition functions of black holes with electric or magnetic charges, and they have this motion in this K1 background. So these guys, in principle, can have area, and they're so-called puffed up by the motion in this K1 background. And finally, we have the Siegel modular forms, the genus 2 guys. We describe ionic black holes which have both electric and magnetic charges and have angular momentum.
Angular momentum is in the fifth direction.
Exactly, the fifth direction.
There's no...
Exactly, in the fifth direction. It's K monopole. And the Fourier expansion coefficients of everything that we've done so far, they tell you about the degeneracies of these black holes as a function of which electric charge, which magnetic charge, and the value of this angular momentum that you're looking at. So this is where the story all comes together. The coefficients are central to our understanding. So you want to ask a bunch of different questions. Well, can you predict the coefficients? And can you recreate these coefficients from supergravity? Okay. And you can also ask a different question, which is that are the partition functions also sensitive to the more intricate phenomenon that takes place, like wall crossing, And the answer is yes, all these things. So let's go into the idea of constructing partition functions. So this is a warm-up example that I often give in considering these talks. A warm-up example is to construct the n equals 8 case, because things are quite clean over here. So we have black holes in n equals 8 for the compactification of string theory. So this is obtained by constructing type 2B string theory in D6. And yes?
So can I ask a question? The slide before wasn't assuming that n equals 8 when you distinguish these three cases.
Sorry, was it what?
This, have you been assuming that you are an n equals 8?
This one, most of the talk will be focusing on n equals 4. So this is like an n equals 4 setting.
And then you run the modular forms from forms.
That's the subtlety that will come to.
But then this is only true for you, right?
No. Okay. If you want to go into the full the thing about this is subtlety which said, like, you get the subtlety from the partition function sensitive to this other data, and that's that's subtly that's hidden inside Jacobi form, the Siegel form, that is you break it to a mock piece. We'll come to this in.
But that's actually only true for equal 4. There is no Siegel modular form.
Yeah, there's no Siegel modular form.
And in equal 4, the counting the double bar Hardy states is a modular form.
Right. Yeah. Okay. It's a subtlety which is embedded into.
You could write neuromorphic Jacobi form with neuromorphic invariances, and then we can do that.
Yeah. So, yeah. So far, I haven't introduced log clustering, so we build up. So. Okay. So the warm-up example you can always look at is we can look at the case of n equals 8 compactification, which is type 2B string theory on T6. And it's a theory in which we want to study these 1/8 BPS black holes. Okay. So the index partition function of these black holes there are of course subtleties in asking, well, how do you look at BPS states and construct energies of T6 because the genus is trivial. So there's a very nice paper which tells you how to construct this. That's by Martin more and Stronger. But you could, in principle, construct the 1/8 BPS states, BPS spectrum partition function for these 1/8 BPS black holes, and that is given by this Jacobi form phi minus 2,1. And the Fourier extension of these guys contains information about the actual black hole degeneracies. So it's just a phase away from the actual black hole degeneracies. So you want to ask the question, well, how do I figure this out exactly? Well, there are two ways. One is that you could really, burn your computer out and start computing this function like case by case by case.
Don't need to burn the computer for this one.
Not this one. Yeah, I mean, this is not a computer. This one will get fried though. So you could, in principle, go and say, okay, let's do Fourier expansion and then go arbitrary Dutch. But instead of doing that, there's a very, very nice analytical mechanism that allows you to do this. This is the so-called Hadith Method method. And basically it tells you that if you want to derive the so-called coefficients of positive discriminant, that is, in this case, the discriminant is 4n minus L squared. So if you want to construct states which have discriminant greater than 0, all you need is information about the modular properties and behavior of the cusps, and access to coefficients which have C delta less than 0. Plug that into a very nice, rather ugly looking expression, and you get out, you can in principle recover all the coefficients on the text. So let's take a quick moment to describe the key parts of this formula. So by the way, this is Z mod 2 MZ. This is the actual reason why the Heisenberg group actually becomes restricted, that you're working in a very nice coset representation. So we are taking input of states which have delta less than 0, and there are these functions known as Kloosterman sums and Bessel function, modified Bessel functions, which come together. And the idea is that you plug in only this guy. This tells you about the modularity properties, and that's just the Bessel function whose weights are determined by your determined by supersymmetry. And once you know those guys, all you need is this piece, and you can, in principle, reconstruct the full spectrum of your. So, going into the full details of this cell, use the computation that might take you about a day or something. But the key idea that you have to remember, we don't focus on too much details right now. The key idea that you remember is that you just feed in delta less than 0 and know a few properties of the system such as modularity, then you can get out all C greater than 0 terms. And these guys precisely, if you up to a phase, remember, these are precisely the degeneracies of your n equals 8 black holes. Okay, but on the gravity side, you could do it a completely different way, right? So the gravity side, how do we do computing entropy? Well, you do it by localizing a path integral. But now the path integral is again a very complicated thing. There's this very nice expression by a set of papers by Ashok, where for these BPS black holes, the partition function of, or rather the partition function was given in terms of the exponential of an object that actually is a Wilson line that wraps the horizon of the black hole. So you can in principle get out the partition function of a given charge Q given by some Wilson line around the horizon. And it's a regularized Wilson line because the volume of ADS2 is going to be infinite. But this is, in principle, a very, very difficult integral to evaluate, right? Because even if you set the AI to things like attractor values, which regardless of what asymptotic fluctuations there are, it gets fixed in the value horizon, it's still a very difficult integral to evaluate. And this is where Val is an expert because he has studied this to death. Still, no, you killed a lot of these problems, so that's great. But are we all alive inside? Really, that's the question, right? The leading term of this expression is, in fact, area law. So if you want to evaluate the full partition function with all the saddle contributions, you could localize it in the sense of Huysman-Heckman, meaning that you convert this infinite dimension integral into an infinite finite convergent sum of I-Bessel functions. Okay, and to do that, it's actually there are a couple of things that one has to keep in mind, which is that you have to construct this localized path integral. We need to figure out what the localized manifold is, and that's of course a difficult thing to do because you want the ones which are that are constrained by a supercharge. But of course, the moment your supercharge is defined on a background that fluctuates, it becomes difficult to do these computations. So you want to, so there's a very nice paper by Val during his PhD where he computed this equivariant version from the BRST operators. And you can find, in principle, the localized manifold by looking at the ones which annihilate the fermions in the theory. So we solve this expression over here. And you're again using the attractor mechanism to set the values to be ADS2 plus S2. And the matter sector comes from understanding the fluctuations of your scalar fields. So with these, each of these calculations itself is, I think, a couple of papers or something in their own right. So, but the idea is that once you have those pieces, you can start putting together the localized path integral. And the localized path integral is something that gives you this expression here, where you're now doing integral over the localized manifold with some appropriate measure, which is itself a difficult thing to compute, times this piece over here and the one loop determinant, which comes from this Gaussian integration on the localized manifold, and the actual contribution from the measure itself. So there are a bunch of difficult pieces that you have to put together. And you also have to construct a bunch of other things to understand, like you have the F term and D term contributions when you look at the n equals 2 superspace action, and the D terms, which are again constructed by David and Patmadas, which like, we don't know if they vanish on localized manifold, but it's conjecture that they do vanish on the localized manifold. But in principle, this is just to give you a flavor of the idea that the entire problem, if you do it in the supergravity side, is not a very it's not a very simple thing to go ahead with. But you could, in principle, start to use results from geometry where you look at, for example, you can compute the one loop term and the actual piece that sits in the exponential part of your localizing integral, where F now is just something that looks like the intersection matrix of the cycles of the T6. So there's a lot of geometry that goes inside over here. But once you do that, you can put everything together and compute the localizing, the localized partition function, which to leading order looks is given by this expression over here. So it's only one Bessel function. And if you look at the Rademacher expansion, this actually corresponds to the either K or the C equals 1 term. So I've used the word C over here, but it's a C equals 1 term in the Rademacher expansion. This expression over here. So in principle, the supergravity, the idea is that if you do the localization correctly, supergravity should start to look a lot like the Rademacher expansion, right? And to start going hierarchical or higher C's rather, you have to construct the whole folds of ADS2. But if you can also just look at the localized path integral at leading order. So can I close this door? Yes. COVID reasons, I should not close that. But if you look at just the Rademacher for the case of for the case of phi minus 2,1, which is actually the BPS partition function of the 1A BPS black holes and n equals 8 compactifications, well, there's only one polar term. So there's only one term that appears in the Rademacher expansion. And you could ask, well, how does that match alongside the actual, the leading order term from the localization path integral? And this is a very nice calculation done by the Parmoti and Robs, which shows that, already the leading term, it looks very much just like epsilon away from the value that you get from the Rademacher. So the degeneracies actually, if you include more and more terms in the localization path integral, they actually start to converge and go closer and closer and closer to the actual value of the Rademacher technique. Okay, so I mean, this is just the leading order case. I mean, I could have included more terms, which you would have seen the convergence a bit more. But for the sake of this talk, this is the key philosophy that you need, which is that if you want to look at the relation between the microscopic side, which is the control field theory side, and the macroscopic side, it's the geometric side of the theory, you have these modular forms or Jacobi forms. So I'm using modular and Jacobi interchangeably over here. The Jacobi forms, the degeneracies of these guys can be encoded in the geometric side by studying this quantum metric function, which is just the expectation value of the Wilson line around horizon with attractor values of the gauge fields and regularized to include the fact that A is to infinite volume. And the degeneracies of black holes here are the Fourier expansion coefficients of the modular forms, the Jacobi forms. And what you get out of this side are the Fourier coefficients of the best functions from the localization of the quantum entropy function. So it kind of tells you there's a very nice relation, at least on the face of it, between what the Rademacher technique can do for you in terms of the supercontrol field theory and what the localization of the quantum entropy function can do for you in the supergravity. Okay? So that's the n equals 8 case. In the n equals 8 case, you still have this nice protected modular symmetry or the Jacobi modularity of Jacobi forms. And it gives you a very nice result, which kind of converges rather quickly to the answer for the Rademacher theory. But what happens when you apply this to n equals 4? Okay, so n equals 4 is a bit more complicated. And the complication comes from the fact that there's more, the modular dependence is not quite clean as in the n equals 8 case. I have about 15 minutes, 20 minutes, right? Okay, so you have this duality between string theory, which allows you to look at this entire model in a bunch of different frames. You can either look at it from the type 2A frame, type 2B frame, or heterotic frame. But what we need to appreciate here is that there are two kinds of Laplace solutions that we can look at. These are the half-BPS solutions for which the partition function is something that you've already encountered, which is this the 1 over delta eta to 34 term. Okay. Then you have the so-called quarter BPS black holes. These are the larger black holes, like here. Okay. Good. So this is a term which we've seen before. It's the Z1 half. It says 1 over eta to 24. Whose partition function is delta eta to the power minus 24. These guys describe black holes, which are either purely electric or purely magnetic. And if you actually do a Fourier expansion coefficient, Fourier expansion of this particular homomorphic modular form, the Cn will tell you about the degeneracies of Q to the n, where n is either electric or the magnetic charge. And there's no subtlety over here because there's no, except the simple code, there is no deep meromorphy in this function. So you can actually do the supergravity analysis rather easily, and it is just done by evaluating the entropy of these half BPS black holes on some attractor contour and some attractor geometry. And this was done in the early 2000s or late 1990s by Gabriel Cardoso, Bernard de Witt, Mohat, and Capelli.
So you have to go beyond supergravity and include higher derivative corrections.
Right, yeah, yeah. But we want to come to the case for large black holes, because this is where things get really, really interesting. So there's a very, constructing the black holes itself is a very nice story number theory, because the starting point is about elliptogenes of K3. And that we've encountered before, it's twice the Jacobi form phi 0, 1. And this admits for you a Fourier expansion in terms of objects known as CK3, which are just the expansion coefficient of the energies of K3. And in order to give the thing was a multiplicative lift, so Bircher's lift of this function, which gives you a function on the Igusa-Casa right, an inverse Igusa-Casa form. So this is basically like taking symmetric products of the string and winding them over and over again, multiplying many number of times, and you're asking what is now the associated partition function in the signal form. And that is precisely this object here, which is given by 1 over phi 10, which has this very nice expression. And of course, this was an object that, you know, it's in Igusa-Casa form. It's the only, well, phi 10 by itself is the only cuspidal form of weight 10 in the Siegel upper half plane, instead of Siegel modular forms. And it's been studied, it was studied studied with great interest in the 90s, particularly by Kawai and applied by Dijkgraaf-Verlinde-Verlinde. And this is going to be central to our conjecture, because this Siegel modular form, 1 over phi 10, as conjectured by Dijkgraaf-Verlinde-Verlinde, so the square over there, so I don't have to write names twice. As Dijkgraaf-Verlinde-Verlinde is that this phi 10 counts all quadruplicate states in the theory. Okay, so that's still unproven. And in fact, this is why I said we don't understand why we have a genus 2 surface, is that we don't understand what the origin of this phi 10 is, why it's so relevant in counting quadruplicate states in this form, string compactifications. Okay, so we can apply the same thing and try to extract the genuses of the black holes from doing the Fourier expansion. And then if you try to do this, you realize that, well, this is not always very clear, because there's a contour dependence of this integral. And the contour dependence is ruined, or it kind of becomes very complicated when you actually take in fact that this phi 10 inverse is a doubly meromorphic function. It's got a double pole at z equals 0 and all the other sp2z transformations that you could do to this point. Okay, so the question is, well, if you have a contour that it doesn't encompass the pole, or one that encompasses the pole, then obviously you're going to pick up the contribution of the residue of this pole. So that means that you're moving your contour along the integration, and suddenly when you cross a pole, there's an abrupt jump in the degeneracy due to the residue. Right? And this is precisely interpreted as what's happening in terms of wall crossing phenomena. So you've got, in principle, bound states of you're basically like when you have a residual contribution and you go away from when you pull your contour away from this pole, then you're in principle losing states because you're subtracting the contribution from your residue, and you're basically no longer counting states which are bound states of half BPS states. So you can have two half BPS states which come together, masked as quad BPS states because it's more energetically favorable at these locations in moduli space. And at the same time, when you go away from this Wallenstein stability, you can, in principle, they decay away because it's more favorable for them to just be two half BPS states. So we have to keep in mind here, there's this sort of two moduli spaces that look at. There's a space of there's a space of period matrices of genus 2 surfaces, and the actual moduli space in string theory. This is the O22,6 moduli space in string compactification. That's where the actual moduli space in Walton moduli stability lie. But the Walton moduli stability in that moduli space get mapped onto poles in this space of in this upper half, Siegel upper half plane. Okay, so that's why when I say z equals 0, you have to stop me and say, well, what the absolute hell do you mean? And that's exactly what's going on. At the same time, you can, in principle, take a quarter BPS state, which is not a bound state of two half BPS states, and that crosses a Wallenstein stability, and it doesn't really care because it's not a bound state, so it's integration basically. So what you want to do is, if you want to really ask, well, what is the partition function that I'm interested in? Well, these guys are already counted in my 1 over eta to 24, right? So why am I counting them over again? So you want to basically remove the contribution from these bound states, and what you're left with is only the contribution of quarter BPS states. And this is also important for us in supergravity because, like, we're only looking at terms which have this areal of contribution and sublinear contribution, which depend on the concept of an area. And we want that to be as universal as possible. And now if you're telling me that, well, I can only do that in a particular region of modular space, that's not a good enough thing. So you want to remove contribution from all these guys, right? So that means you want to stop overcounting, quantity states. So what do you do? I'm already laughing because I'm giving a teaser for what's going to happen. If you want to stop the count, wise man, not really, but so basically you want to stop counting these happy states. So how do you stop counting them? Well, the way to do that is there's a very nice number theoretic way to do it, which was done in this paper by Atish Samimurthy and Dan Zagier. And the idea is that you take the residue at all these poles and you average over them, right? And from the averaging function, you can construct a mock Jacobi form, which in principle has all the meromorphic properties of this original Siegel modular form, right? So that means you break down, you do the Fourier Jacobi expansion. You don't do the Jacobi Fourier expansion, do the Fourier Jacobi expansion, and break down this Jacobi form, because you see the modular the meromorphic variable is z. I mean, that's a troublesome variable. So this PM we don't care about at this point. What this also has a physical consequence, because what that means is that this is what you do in string theory anyway, is that you treat your when you want to do analysis of charge by charge analysis of black hole string theory, you treat one of them in a grand canonical ensemble and one of them in a microcanonical ensemble. You fix one charge, either electric or magnetic charge. In this case, you're doing it for magnetic case, and with the electric one fluctuate. Okay, so you're treating one in the microcanonical ensemble, and the other one is going to be the grand.
Actually, some over all.
Yeah, we eventually do some of them, but when you do it term by term, right? When you do it term by term, this for once you set what psi m is, that's fixed, right? So that's fixed in terms of what the value of m is. So this is why I said you get this whole parameter of family of parameters of Jacobi forms, which are given only by the magnetic charge of the black hole. Okay. Now you could, in principle, repeat the same course again, but instead of doing it for the Siegel upper half plane, you do it for the upper half plane. And this very nice result by Dan Zagier allows you to write this function down. So this is not an arbitrary choice of function. There's a well-defined canonical choice of writing this down, which breaks it into a meromorphic mock Jacobi form. Again, it's just a modular but Jacobi form. And this becomes a polymorphic mock Jacobi form, mock modular Jacobi form. And this is where you expect all the Siegel center, or the guys, all these black holes to lie. So here, the quarter BPS states, which do not have a sort of Wolfram. But this is where you would expect the terms which do cross the wall to lie. Okay? And in fact, this is it's a function that's quite easy to quite useful to look at, because you see there's this. It tells you that one of the things that we have to understand is that when you have these dionic black holes that decay at a wall of marginal stability, what you're actually ending up with is two half BPS states. And we know what the partition function of these half BPS states actually are. So it's going to be two delta eta functions. Okay. And this is it's a very nice weight that you actually, it's weighted by the contribution from the two delta eta functions that you take out. And in fact, this is what in math is known as the Appel-Lutz sum, which you derive from the averaging function of all the double poles of phi, well, phi minus, I'd say minus 10, but it's phi inverse of 10. But this guy actually is also it's basically saying you're removing the motion away from the K canonical background. So this guy also has a physical meaning for you, right? So once you actually have the notion of what this psi MP is, right, you could actually subtract from it what psi from this psi m, and you get out what is known as psi m. It's a finite term, or the finite holomorphic part of this mock Jacobi form. You could still do a T transformation, okay, because the mockness comes from the fact that you ruin your S transformation. T transformations are still quite well defined, so it's still a periodic function. So we still do a T transformation of this holomorphic mock Jacobi form, And you would expect that the Fourier coefficient that you get out from these CF should give you the single center of black hole degeneracies. And you want to ask, well, can you do this in supergravity case, meaning that can you capture it in terms of an attractor mechanism in supergravity? Right? So if you actually want to do this in the attractor side and also the black hole side, there are two things that you have to remember. I'm getting very close to my time limit, so I'm going to slightly speed up.
I think you have 5 minutes.
Yeah.
Started a bit late.
Okay. Okay. So the idea is that, remember when I said you have these two things. One is that you want to recover the degeneracies exactly from the field theory side, and then you want to repeat this in an analogous way on the supergravity side. So you have the Rademacher technique in superconfound field theory, and you have the localization technique. And in the case of understanding where the Rademacher plays in, it's also important to understand how to source those states which would have negative discriminant, where the seed of these lack of partitions actually come from. And in fact, that is a very non-trivial way of looking at it. And in fact, this was why we were motivated to understand it, because it was in a paper which was written by Val and Samira that we understood that there has to be some intricate structure to seeing where the negative discriminant states actually get sourced from for the n=4 case. Well, you could try to ask. You can first set the value of the contour to be the special attractor value, because there's a contour dependence in Siegel modular form. We set that to be one which has some relevance in supergravity, and you want to ask, okay, where in this contour do my negative discriminant states come from? And it turns out that they are given in terms of the so-called fairy circles, where only a bunch of these fairy circles, you've probably seen all these fairy circles, because if you look at the modular upper half plane, you're going to see these lines which are going by infinity and all these different semicircles, right? And basically only a bunch of these semicircles, a bunch of these sets, they tell you about, they give seed these negative discriminant states for you. And there are two ways you can characterize a set. One is to really do a brute force analysis and ask, okay, do these states, do these so-called semicircular walls of marginal stability give you something sensible? And we do that ad infinitum. We didn't do ad infinitum, but you can repeat that over and over again. And you can ask, well, is there a product of this way of doing it? Meaning that you look at all the decay channels from all these different semicircles, and you see which one give you sensible answers that can eat us, and you count only those guys. Or there's a very nice way of doing it, because once you've identified which semicircles should in principle give you, see the negative discriminant states in the so-called region R. This is the region that corresponds to supergravity for you. Well, you can ask, okay, is there a much nicer way? Because you're asking, well, you have contributions from smaller and smaller semicircles that enter your, that give you contribution in this particular chamber over here, or this particular region in modular space. So once you identify those walls, actually there's a very nice paper by W. Cardoso, Oscillation on Fourier and Cello, which told you that, well, you could do this very nice particle physics-y type of thing, but you could do it in a more topological way, by actually just considering so-called continued fractions. So continued fraction is a theory that goes back all the way to Ramanujan, which is that you write down, take a fraction, and you write it as continued fractions over and over again. And the meaning of topological is also because there's this huge relation between what continued fractions are and what length space invariants are for solid tori. Okay, so there's a very nice paper by Kirby from Berkeley, if you're interested in reading about this way of how continued fractions relate to these length space invariants, and these are the ones which also enter these orbital babies too, by the way. But anyway, that's okay. But the idea is that once you know where to look for these kind of terms in your moduli space, you can actually start feeding them into your expression for what the Rademacher expansion is. So you could take the coefficients which are related to degeneracy of black holes, and you feed in only the terms which have negative discriminant. But this is no longer as simple as the one that looks in the n=8 case, because the n=8 case you only had something that was modular, but here you also have contributions from modularity. And this was a very nice result that was derived by Francesca and Valreis, based on some earlier work by Maxhart and Brinkman. But the upshot here is that you could, in principle, try to construct the black hole entropy from just knowing what the degeneracies, negative discriminant degeneracies are for that particular psi n f. That's the only thing that you need to know. And in principle, you could do this for this whole one parameter family, and you could reconstruct the whole part of the state. But there's also a nicer way of doing it just from the Siegel modular form itself. We won't go into that because that is a different thing altogether, and somebody else might be able to get better than I can. But the question you want to ask now is, well, the partition functions for these quantum states are actually not modular forms. In the case of n equals 8 supergravity, there's a very clean way of doing it. You have this very nice way in which you say, okay, I've got my, sorry, maybe I take two more minutes, okay? You have this whole, the very nice localization, which feeds in through connects to number theory, and then the Rademacher technique, and the degeneracies get mapped onto one another. But you want to ask, well, in this case, it's a bit more complicated because what gives you the localizing path integral? And this is pretty much the motivation of what we're trying to construct right now. Okay, so can the microscopic formulation firstly help understand localization better? Right, because localization is sensitive to, in the case that we have known so far, it's sensitive to something only that looks like a leading order term over here. Right, so only the leading order is reproduced by localization for these Mach pieces. And maybe a question here is to ask, well, we have a particular choice of contour over which we have done the integration. Does that help you understand which contours to actually do the integration over in supergravity localization? And more importantly, this is the million-dollar question that we're working on, which is how and why does the Mach modular nature of a black hole arise in supergravity? There's a priori no reason why this rather interesting but also rather weird symmetry arises in supergravity. So this is part of the work in progress. So let me give you a quick upshot, a quick overview of what in principle we're trying to achieve. Well, you could try, yeah, really.
Maybe it's good to.
Okay, okay, I'm wrapping up very quickly now. You could basically ask, like, which parts of the localizing path integral can you actually change? Well, you have to compute the measure properly. You can compute the one loop determinant, which we know is equal to 1, but you can also look at this contribution to potential is received higher derivative non-holomorphic correction, so on and so forth. And in principle, you could try correcting the potential, correcting a bunch of terms in supergravity, but let me actually skip straight to the end. The idea is that we want to now look at different ways in which you reconstruct both these terms of supergravity. We have an understanding of where the blue pieces come from, right? But we're trying to correct the supergravity localization to actually make sure that these two places also match to each other, which is that supergravity matches this closed-amount piece, and it gives you this ibis piece over here. So I think I'm very much over time, but I'm here until Saturday night or something, so please feel free to ask me questions. So there is some hidden number theory in supergravity, but the question is how do we actually extract it out completely? And modularity should be apparent, but how or why is still work in progress. So with that, I'll stop and I'll take any questions. And if you have more questions in detail, you can ask me later.
So we have maybe time for one or two questions. I'm not sure I understood how you clarify the notion of this negative singular state in supergravity. So is it that when you put the effective action, which has already the Moore-Hervé term, this Moore-Hervé term, the R-squared term with a lot of deducting, is that this one that actually you can interpret then as a sum over the negative delta state? Or is it something else? I'm not trying to.
I sort of lost your question halfway. Could you say that again, please?
So, well, let's put it in another way. You said that you understood in supergravity, which is the source of the singular state.
Oh, no, we have to understand that.
You have to.
We have to understand that. But we don't understand.
Well, the full partition function, it's clear what the source is. It's the two-center.
No, it's a two-center.
I'm thinking about multiplication and supergravity, where
In supergravity, hints of it, it's not the full negative discriminant state. The parts of it are indeed built, as you said, from just the Harvey Moore correction and the free potential, and then when you localize,
Harvey
you come
Moore.
downstairs,
Harvey.
and they give you each of the 24 Fourier coefficients. You can re-expand.
Yeah.
But it's not the full formula for the negative discriminant states is still a work in progress.
Yeah. The lots and lots something you have to address over there.
But the higher derivative correction in the free potential will for sure create.
yeah, because they typically goes that way.
Yeah.
The other question online?
I don't see any questions online. Okay, so
So as Abhiram was saying, he's there for a couple of days.
you can ask me the questions.
Sure, thank you very much.
Thanks a lot.